Welcome to another episode of The U. My name is Kyle Winters, Technical Advocate at Cisco, and today I want to talk to you about eBPF. We'll get started by giving you a high-level refresher on what the Linux kernel is, and then dive into eBPF, its benefits, and some use cases for it. Then we will dissect and run a simple eBPF program so you can gain a better understanding of how it works. And lastly, we will review and run a program to perform packet filtering on a Linux host, all while using eBPF. If you'd like to follow along, check out the free tutorials that cover the content in today's episode and more on Cisco U. So let's jump right in. Most of us are familiar with how to interact with and operate computers in the user space, and that includes things like web browsers, text editors, the Linux terminal. There's also the physical hardware too. And that includes things like network cards, memory, storage, disk, keyboards, etc. Applications in the user space need to be able to talk to the physical hardware, but it can be rather complex for them to know how to directly communicate with all the different types of products and vendors that exist in the market. There are a lot of different vendors that make physical hardware, and it's a bit complex for the user space to know how to properly communicate with those different components. That's where the kernel space comes in. It sits in between the user space and the physical hardware, allowing for a normalized way for these two to effectively communicate. But what if you need to make changes and extend the capabilities of the kernel space to do new and unique things? That's where eBPF comes in. It originated from the Berkeley Packet Filter and was at first called the Extended Berkeley Packet Filter, but that acronym has since been dropped because eBPF can do so much more than just packet filtering. It's a safe and efficient way to extend the functionality of the Linux kernel and add new capabilities into it without requiring any changes to the kernel source code. eBPF is easy to use and can be embedded into high-level programming languages like Python. It runs fast, thanks to its just-in-time compiler, and it has security built in that allows for safe execution. When it comes to network security, eBPF has incredibly valuable application in areas such as advanced packet filtering, DDoS mitigation, intrusion detection and prevention, runtime security enforcement, data exfiltration prevention, and even application sandboxing. eBPF works by loading small programs into the Linux kernel, which are written in a very restricted version of the C programming language. The programs are compiled directly into eBPF bytecode that is suitable for kernel-level execution. These programs can attach to various hooks in the kernel and run in response to specific actions, which include system calls, function entries and exits, kernel trace points, network events, and more. When an eBPF program is triggered at its hook point, it can call a helper function, which is a special function that enhances eBPF's capability by performing a wide array of tasks such as searching, updating and deleting key value pairs and tables, collecting and flagging metadata, performing tasks with sockets such as binding, retrieving cookies, and redirecting packets. You can even chain eBPF programs together using helper calls. I mentioned just now key value pairs in a table, and that's what an eBPF map is, a key value store where values can be treated as any type of data. A vital aspect of an eBPF program is the ability to share collected information and to store state. For this purpose, eBPF programs can leverage the concept of eBPF maps to store and retrieve data in a wide array of data structures. eBPF maps can be accessed from eBPF programs as well as from applications in the user space itself via system calls. Here's a simple Python script that is executing an eBPF program to trace system calls. You can see we start by importing BCC, which is a set of tools and libraries that helps you monitor and analyze the performance of a Linux system by using eBPF. Next, we have our actual eBPF program, written in C and stored as a string. This will handle the eBPF logic for us, which in this case will print a new message when a new directory is created on my Linux machine. After that, we have the code that loads the eBPF program and runs it. And lastly, we have an event loop that will continuously monitor and print the trace messages for us to standard out. Let's go ahead and test this out in my lab environment. So as you can see here, I have a Linux host, Ubuntu-1, And I'm going to go ahead and run an eBPF program that I wrote in Python. So I'm going to call sudo python3, and then the program itself is called eBPF-system-calls. Enter in my password because I am doing this with sudo. And you can see it's ready to go. So on the right side here, I have another terminal window open to the same server. And I'm just going to go ahead and create a new directory, and let's just call it test. And you can see the eBPF program recognized that and wrote it to standard out. You can extend this even further by writing to log messages or log files and being able to really monitor a system effectively using eBPF. Next, I want to show you a more advanced demo of eBPF where we will perform some packet filtering on a Linux host. We have two hosts in my lab environment, one of which will be our source and the other our target. Normally, communications like SSH and ping will work just fine between these two hosts. But when I run my eBPF program on the target host, I will be able to filter out SSH and ICMP packets from the source host, effectively blocking communication from the source to the target with these protocols. It works by reading the packets as they come into the Linux host running the program, specifically examining the IP headers and the TCP UDP headers. The relevant data points, such as the source and destination IPs, the source and destination ports, as well as the protocol used, are then extracted and put into an object. This data is then checked against an eBPF map that contains a list of IP, port, and protocol combinations that we should filter out on. If our packets match, then our eBPF program drops the packets and the communication between the hosts is effectively not allowed. Let's jump into my lab environment now and see this in action. So, as you can see here, I have two Linux hosts now. One is Ubuntu-1, which will be our source, and the other is Ubuntu-2, which will be our target. I'm going to go ahead and run some pings really quick just to show you how this does indeed work currently before we run the eBPF program. So I'm going to ping it at its IP 192.168.9.131, and you can see this ping is going through successfully. Now, if we wanted to SSH to this host as well, let's go ahead and SSH Kyle at 192.168.9.131. And you can see it's prompting me for my password, which I will enter. And now I've effectively logged in via SSH to this host. Now let me go ahead and exit this and let's run this again. But let's first run our eBPF program on our target host. So let's go ahead and do sudo python3 eBPF packet filter.py. So I'm going to go ahead and run this, enter in my password since we are running this as sudo. And it is now running and monitoring that network traffic. At any time a ping or SSH comes in from our source host, it shouldn't go through. So let's jump back over here and let's run our ping command once again, ping 192.168.9.131. And as you can see, these are timing out. They're no longer going through, just like they were before. So as you can see, effectively ICMP and ping are no longer working between these two hosts. Let's go ahead and try that SSH again now. SSH Kyle at 192.168.9.131. And you can see as well here, this times out and will no longer work. So this is a great way to essentially do packet filtering and block specific types of packets from specific hosts, leveraging eBPF as well. If I go ahead and kill this process and kill it in the target host as well too, try to do the ping again, you can see this is now going through. So eBPF is a great way to do things like packet filtering, and there's a ton of other use cases for it as well too. Hopefully this was a fun and informational episode for you. If you're interested in learning more about eBPF, you can head to ebpf.io or check out one of our free eBPF tutorials available today on Cisco U. That's u.cisco.com. Thank you for watching, and I'll see you again soon on the U.